Hi students, welcome back. Lesson 14. Let's do a separate example. The first three videos have all been Cecil College smoking. Let's move on to greener pasture, something new. Video part D. What this whole lesson is about, it's one example start to finish of working with a sampling distribution for the sample proportion. Alright, you probably notice a lot of blank space in your notes. We're going to fill that all in with good information. One polling group indicates 1.2% of adults in America can be classified as compulsive gamblers. Let's investigate if the proportion has changed. Here in Maryland, we're anticipating an increase. As you probably know, there used to not be casinos anywhere but Las Vegas and Atlantic City, and over the last decade or so, there's basically casinos within 50 miles of every person in America. There's a bunch in Maryland now, Delaware, of course, New Jersey, Pennsylvania, West Virginia. So possibly more people are compulsive gamblers just because it's available. All right. Aside from that, we have lotteries now that weren't around 10, 15 years ago. Powerball and Mega Millions and all this. Researchers collect a random sample of 1,200 Marylanders. Okay, so there's our random sample. Flip the slide here. It says Part A, determine the correct model for the sample proportion, check conditions, draw, and label the model. There's a lot to do here. Okay. Before we get going, we'll always check conditions, so we'll do that first. Probably a good idea at the top. Lowercase n sample size for this problem is 1,200. And let's see. We'll start this whole thing by assuming that p equals 0.012. That's the 1.2% problem gamblers. Now again, we're investigating. Maybe there's a change in Maryland, but we found this study in a journal or a newspaper or something. So we'll go with this until the data convinces us otherwise. First things first, we do need to check those conditions. We're going to do a real good job of this on the videos. I mean, this is your textbook, so we're not going to take any shortcuts. We're going to make sure that I don't get lazy and just say them. I'll write them down, and you need to write them down in your workbook. Number one is the variable categorical. And so the question we're asking people, or giving them a test or an assessment, is are you a compulsive gambler or not? That's categorical. So it's like a yes-no question, right? Compulsive gambler or not. That's what we're measuring or tallying up for everybody. That is categorical. All right, that's the first thing that we need to check. So we're good there. Number two, let's see. We need to have an unbiased or a random sample. We're told in the problem it's a random sample. So I'll just note that down. We're told that the sample is random. 2 for 2. I bet we're going to be 4 for 4. Why would we give you a problem where the conditions aren't met right to start? So we'll move on to 3 here. Number 3 is that sample size. The sample size needs to be less than 10% of the population size, and we definitely have that. N equals 1,200 is certainly less than 10% of all Maryland adults. A lot of people are surprised, but I looked it up. There's over 5 million people that live in the state of Maryland. So 1,200 is certainly less than 10% of the 5 million. And then finally, do I expect, if I sample 1,200 people, and I expect 1.2% to be compulsive gamblers, is that more than 10? Do I expect more than 10 people to have a gambling problem? You might automatically assume it's met, but it's awfully quite close here, right? So what we can check is n times p, sample size times p, so 1,200 times 0.012 is actually just 14.4, and so it's barely over 10. Right, out of 1,200 people, we're not going to expect hundreds to be compulsive gamblers. So, and this exceeds 10, so we're good. Remember, we checked this one to make sure that a normal model is going to work. Okay, so don't forget. Now, of course, with 1,200 people, if 14 are compulsive gamblers, then like 1,185 won't be. That's way more than 10. Just to make sure, I don't want to be lazy on the video. We're putting this permanently on the internet. N times 1 minus P would be 1,200 times 1 minus 0.012. That's way more. That's about 1,185.6, I think. Yep. And that's, I'll just put, that's definitely greater than or equal to 10. And so all 4 conditions are met, no problem. Variables categorical, sample we're told is random, sample size is less than 10% of the population, and we've got at least 10 and 10 successes and failures. All right, whole slide of writing, we haven't even started the problem yet. Let's start the problem now. All right, pause it if you need to. I got to clear some space here. Because conditions are met, what's the proper model? Proper model will be normal model. I don't know, maybe I'll put it up here. So now we know that it's going to be normal model. Okay, with the normal model, I need the 2 parameters, mean and standard deviation. The mean of p hats equals p, and we're going to presume before we collect the data that, hey, in Maryland, no different than nationwide, 1.2%. Okay? Standard deviation, sigma of p hat. That's this formula. To save space, it's p times 1 minus p over n, whole thing square rooted. I'm just going right to the numbers. You can flip back a page or two if you need to see the letters and symbols, but this is p, 1 minus p, all over n. So p is 0.012. 1 minus, divide by 1,200, square root that thing. To keep it clean, I'm just going to round this to 0.003. So this is about 0.003. There's many more decimals, but I got to draw this normal model and label it. So we're going to keep it like that, or it's going to get messy on the horizontal axis. All right, let's draw this thing out. Put here. This is the p hat model. Now, I've never written this before, but just keep in mind this is the I don't know if I spelled it right, but that's the theoretical model. This is the model that, if my assumption's correct, 1.2% problem gamblers, this is the model that will sort of govern how p hat behaves in repeated samples. Okay? We're cooking this up based on that assumption. The model's either right or wrong. Once we collect the data, then we'll make a determination, was this a good assumption for Maryland? Okay? What goes in the middle? The mean, 0.012. And we'll do 3 tick marks here. So here's 1, 2, and 3. To the right, we'll go down same distances, 1, 2, and 3 to the left. I'm jumping up by 0.003s. Okay, so keep the numbers a little bit cleaner. 0.012 plus a 0.003, this would be a 0.15. If I go 1 more, it'd be a 0.18. And if I go 3, it'd be a 0.21. I hope. Take a little peek here. All right, good. If I go, now I want these all diagonal so it looks the same. There, it's a 0.12. I subtract the standard deviation, I'll get a 0.09. I'll subtract again for 0.06. Subtract again for 0.03. So there's the labels, plus or minus 3 standard deviations. You can see why we rounded this to 3, because crazy decimals here. Put this, sure. If I go plus or minus 1 standard deviation, we know that that's 68%. If I go plus or minus 2, it's 95%. And plus or minus 3 is 90.97. I didn't leave myself much space. Squeeze it here. 99.7% of the time. This would be with repeated samples. Theoretically, what if I took a bunch of samples of 1,200 Marylanders and gave them a test to determine if they're compulsive gamblers? Just think how expensive this is and hard to collect that data, right? The theory helps us make decisions based on the one sample we'll collect. So we're going to understand this theoretical model here. All right, I think we've done it, right? Check the conditions, draw and label the model. Here it is. Let's check the notes. Anything I forgot? Doesn't look like it. All right, if we flip the page, a couple questions to ask. That's a pretty good picture. I don't want to erase that. Maybe we'll get rid of the mean here. Don't forget what it is. We'll clean up some space here. And let's answer question B at the top of the next page. Turns out only 15, I don't know about only, but turns out 15 adults were classified as compulsive gamblers in the study. This would actually happen. Determine the value of the sample proportion. So for part B, this is the actual data. This is the one sample that we've collected. The researchers gave 1,200 gambling assessment tests. Actual data, p-hat. Okay, this is p-hat. This is the p-hat model, the theoretical model. This is the actual p-hat. 15 compulsive gamblers, 1,200 adults. 15 out of 1,200 is, I don't know what, but I wrote it down. 0.0125. 0.0125. It's about 1.25% is what that is. Okay? Now just think, common sense. I'm trying to determine if things are different here in Maryland. Are you convinced that things are different in Maryland? Where does this 0.125 fall on the model? Right? Is it way up in the tails? It's not, right? Isn't that awfully close to 0.012? I mean, here's the theoretical model, and here's sort of where the data came for Maryland. Are you convinced? Was this unusual? Was this a crazy sample? I'm not. Now, we're going to formalize this. We'll look at z-scores and probabilities, but right away I can tell I'm well within one standard deviation. I know p-hat's going to vary, sample to sample. I can't expect to get exactly 0.12 every time. And so this is not unusual. This is like, I'm not convinced to change my mind, and I'm probably going to continue believing that, hey, in Maryland, the 1.2% is a great estimate for the whole state of Maryland. Nothing's telling me different from the data. Okay? But for part B, this is, determine the value of the sample proportion. Here it is. If you move to C then, convert the sample proportion to a z-score, comment on its value. So, how many standard deviations is p-hat above the mean? Not many. I don't know what it is, but here's the formula, right? So the z, with symbols this time, I'm going to take my p-hat, I'm going to subtract off the mean of p-hat, and I'm going to divide by the standard deviation of p-hat. So the z is the same z you've been working with, it's just the symbols are different, the ideas are the same. So plug and chug, take the p-hat, we'll work with decimals. So for p-hat, 0.0125. I subtract the mean, what we thought it was to start, 0.012. I divide by the standard deviation, which was what? 0.03. Remember we calculated that before, or 0.003. So divide by 0.003. Make sure you get both zeros in there. That'd be a huge difference in z-scores if you missed a zero, like I said the first time. All right. Calculate this out. I get a positive number. That's fine. It's positive. It is above the mean, slightly. And this turns out to be 0.167. What's unusual? More than 2, either direction. What's rare? More than 3. What is this? This is 0.167. So this is telling me that our p hat is 0.167 standard deviations above the assumed mean. Remember, we assumed, so I'll put above the assumed mean of p equals 0.12. Our data is right in line with our assumption. There's nothing to change my mind. You'd be crazy to say, oh, based on this, I know that more people gamble compulsively in Maryland. It's just not there. Okay? So again, our p hat is 0.167 standard deviations above the assumed mean of the 0.012. Down at the bottom, part D, and that'll be it for today. Using the normal model calculator on StatCrunch, determine and comment. All right, so here's D. Let's see. I guess we're going to just sort of get that out of there. Get this. Here's the z-score. I want you to make the connection in your head. Like, that z-score is very close to 0, so the probability of getting that z-score should be fairly high. All right, so make the connection. Parts C and D go together. Could ask it in two different ways. Here it is, using the normal model calculator on StatCrunch, determine and comment on the probability of our collecting a sample like we did. Like we did. What did we do? We did a p hat of 0.0125. That's what we did. Or one even more unusual, if our normal model, based on the 1.2% problem gamblers, is a good model for Maryland. All right. This picture is so nice, I'm just going to get rid of this stuff here. I'm presuming at this point you can go to StatCrunch, pull up the normal model calculator, and shade. I'm not going to show you on the video, but I'm going to talk you through it. So here's that normal model again. Oh, if I drew the line just off center, see that dot? I mean, this is p hat of 0.125. And I'm going to shade up. Now, to make it easy, we'll just shade up. There's a little trick maybe we could work on in class or something like that. For this video, what's the chance that, say, I take a sample and I get this percentage of problem gamblers are even more extreme, bigger? And so we'll just shade up this way here, okay? If you shade that on the normal model calculator, it better be pretty darn close to 50%, right? It's almost exactly half. So we'll do a stat button, normal model calculators. Fill in the mean and standard deviation on StatCrunch, put greater than, and it's greater than 0.0125. And if I shade that, here's the answer. It is, if I can find it here, 0.4338. So the probability of, let's say, getting p hat equal to 0.0125 or even bigger so that big probability there is a 0.4338. Squeeze it in there. Almost a 50% chance. The z-score was not unusual. The probability is not unusual. Right? You get a sense with a big z-score, my data gets pushed out to the tails and that probability gets small. Here, my data is very close to the center, that probability gets big. That's telling me something. All right? So, let's see here. How can I summarize this to finish? Since this probability is not unusual, since this probability is not, underline, not unusual at all, we really have no evidence to change our minds. We have No. Underline no. We have no evidence that the, I'm just going to keep going into the corner here. We have no evidence that the proportion of compulsive gamblers in Maryland differs from the 0.012. Okay, so that's fine for this one. Let me just get that in. Since this probability is not unusual, the 4438 at all, we have no evidence that the proportion of compulsive gamblers in Maryland, guess what, I gotta use this one, over here to the side here, differs from our, remember at the beginning we presumed, from our presumed 1.2%. Okay, so maybe we were applying for a grant to get government funds to start building gamblers' anonymous halls and fund meetings and things like that. There's really no evidence that there's a problem in Maryland that differs from the rest of the nation. So if we were going to try to use that as ammo for our grant proposal, we just don't have that ammo. This data is telling us that we're no different than basically everybody else. Okay? What would convince us that we were different? If that p-hat, you collect the data and that data falls up in the tails or down in the tails, then you should start to get the sense that when you're out in the tails, that's telling us that, hey, that data is differing from my assumptions. I've got some ammo, some evidence to change my mind. Okay, but here we don't have it. All right, so that's the second example. Kim Shepard is going to come back with a third. Then we'll wrap it up and we'll move on to confidence intervals. All right, thanks for watching. We'll see you in class.